It's easy to look up at a plane, whether it's a massive jetliner cruising above the clouds or maybe a small Cessna buzzing overhead and just sort of take flight for granted. We see the magic, but we rarely stop to think about the really intricate dance of engineering happening beneath the surface, especially in those, reciprocating engines.
Yeah, it's true. And while jets definitely grab the headlines for commercial travel, the humble piston engine is still the absolute workhorse of general aviation. They power flight training, crop dusters, small cargo planes, so many other crucial applications. Today, we're cracking open Module 16 of the E&C Part 66 Aviation Maintenance Technician Certification Series. It's a remarkably comprehensive guide, and we're going to sort of distill its wisdom to reveal the incredible mechanical wonders inside these engines.
Yeah, our mission for you today is really to pull out the truly essential insights, those surprising facts, and maybe get those genuine aha moments, the kind that transform you from just an observer into someone who truly understands how these engines breathe, how they burn fuel, stay cool, lubricated, and precisely controlled. You'll feel like an insider, hopefully, without getting bogged down in every single technical detail. Let's peel back the cowling. So let's start with the absolute basics. When we talk about how an engine does something, we often hear terms like work and power. How do these actually relate? And, why are they so fundamental here?
Right, okay. So, at its simplest, mechanical work is really about moving something. It's just force applied over distance. Imagine pushing a heavy box across a room. The effort you exert and how far that box actually goes, that's work. In aviation, and often in the U.S. system, we measure this in foot-pounds, or FT pound. It's basically a measure of the total effort that's been expended. Now, power. Power takes that idea of work and adds the element of time. It's the rate at which you do the work. So if you push that same heavy box across the room, but you manage to do it twice as fast, well, you've exerted twice the power. This is actually where horsepower comes from. James Watt, the steam engine pioneer.
Right, I've heard the story.
Yeah, he famously observed that a strong workhorse could perform about 33,000 foot-pounds of work in 1 minute. And that became the definition of 1 horsepower, or HP. So an engine isn't just doing work, it's doing an immense amount of work very, very quickly. That's power, and that's what actually gets an aircraft off the ground. It's also equivalent to 746 watts, by the way.
That makes perfect sense. Work is the total job. Power is how fast you do it. And that power comes from this continuous, synchronized internal dance. Let's talk about the 4-stroke cycle. That's the most common operational heartbeat, right, for these engines.
That's right.
How does this cycle, with its distinct steps, translate raw fuel into usable power for flight?
Okay, the 4-stroke cycle. It's really an ingenious design that transforms the chemical energy locked in fuel into mechanical motion. It involves 4 critical sequential movements of the piston inside the cylinder. First up is the intake stroke. Picture the piston right at the very top of its travel. We call that top dead center, or TDC. As it starts moving downwards towards the bottom dead center, or BDC, the intake valve opens wide. This creates a vacuum, basically sucking in a fresh mixture of fuel and air into the cylinder. It's like the engine taking a deep, deliberate breath.
Okay, intake, it breathes in. What's next?
Next is the compression stroke. So once the piston hits BDC, the intake valve snaps shut, sealing the cylinder completely. Now, as the piston moves back upward, from BDC back to TDC, it forcefully squeezes that fuel air mixture into a much, much smaller, denser space. This compression is absolutely crucial because it concentrates the energy, making the mixture far more volatile, more powerful when it's ignited.
And the timing here is critical, right? The spark doesn't happen exactly at the top.
Exactly right. Here's a key detail. The spark plug actually fires before the piston reaches TDC, typically somewhere between 20 to 35 degrees early. This gives the combustion process a head start, ensuring that by the time the piston actually passes TDC, the burning gases are already building immense pressure, ready to push it down forcefully. And the compression ratio, which compares the cylinder volume at the bottom, BDC, to its volume at the top, TDC, is vital here. A higher ratio generally means more compression, potentially more power, but it's also limited by the type of fuel you can use to prevent something called pre-ignition.
Got it. So compress the charge, light it just before the top, then comes the bang.
Then comes the power stroke. Yes, this is where the magic happens. The compressed fuel air mixture, ignited by that spark, explodes. The rapidly expanding gases create immense pressure, driving the piston forcefully downward, from TDC all the way to BDC. This violent push is what generates the engine's mechanical energy. It directly spins the crankshaft and ultimately the propeller. This is the exact moment where heat is converted into the actual useful power that propels the aircraft.
The money stroke. And after that, you've got to clear it out.
You do. Finally, there's the exhaust stroke. As the piston reaches BDC after that power stroke, the exhaust valve opens up. The piston then travels back upward from BDC to TDC, essentially sweeping out all the burned gases from the cylinder and pushing them into the exhaust system. This clears the way for the next fresh intake of air and fuel, starting the whole cycle over again.
It's like a perfectly choreographed ballet, just constantly repeating hundreds, maybe even thousands of times every single minute. To think of the precise dance happening so rapidly, it's truly mind-boggling.
Now, not all engines follow this exact four-stroke rhythm, do they? I know some aircraft, particularly maybe simpler, lighter ones, use a two-stroke cycle. What makes them different, and what are the trade-offs involved?
That's a great distinction to make. Two-stroke engines operate on a fundamentally different principle. They often prioritize power-to-weight ratio and mechanical simplicity. One of their most unique characteristics is definitely how they handle lubrication. Unlike four-stroke engines with their dedicated oil sumps, two-stroke engines typically mix lubricating oil directly into the fuel.
Right, like a chainsaw or an old motorcycle. Exactly. As that fuel oil mixture enters the engine, it lubricates key components connecting rods, bearings, cylinder walls. The obvious trade-off. Well, this oil is literally burned during combustion. It contributes to exhaust emissions and, of course, requires constant replenishment with the fuel. Another defining feature is the absence of traditional intake and exhaust valves in the cylinder head. Instead, two-stroke cylinders have these precisely machined ports right in their walls. The piston itself, as it moves up and down, alternately unblocks and blocks these ports. That's what controls the flow of the fresh fuel air mixture coming in and the burned gases going out. Because of these ports, the piston rings in a two-stroke engine are pretty unique. They're pinned in their grooves.
Pinned? Why is that?
Well, it prevents them from rotating. If they rotated, the end gap could snag in one of those ports, which would lead to, well, catastrophic engine failure pretty quickly. You also won't find specific oil control or scraper rings on these pistons, since the oil-fuel mix handles the lubrication job. The cycle itself is incredibly efficient in terms of power pulses per revolution. As the piston moves up, it creates a vacuum below it in the sealed crankcase, drawing in a fresh fuel or oil charge. Then, as it moves down after ignition, it first uncovers the exhaust port, letting the burned gases escape. And then almost immediately after, it uncovers the transfer ports. This allows the compressed charge that was waiting in the crankcase to rush up into the cylinder. This fresh charge actually helps push out or scavenge the remaining exhaust gases, preparing the cylinder for the next compression and power stroke. It's a continuous overlapping process, delivering power with every single downward stroke of the piston.
That simplicity offers a huge practical advantage then. Two-stroke engines are often significantly lighter for their power output compared to a four-stroke. That's a massive win for light aircraft where, every pound truly counts.
Absolutely.
The trade-off, however, seems pretty clear. Their time between overhaul, or TBO, is generally much shorter. So you're looking at more frequent maintenance, basically, in exchange for that weight saving.
That's the balance, yes. Lighter weight, simpler mechanics, but typically a shorter service life between major overhauls.
Okay. So beyond the internal cycle, engines also come in various physical configurations. And this influences everything from the aircraft's shape to its performance. What are some of these key arrangements we see?
Yeah, the way the cylinders are arranged, the engine configuration, greatly impacts the aircraft's design, its aerodynamics, even how well it cools. You have inline engines, for instance. These place cylinders in a single row, often an even number, all sharing one crankshaft. They can be liquid-cooled or air-cooled. If the cylinders hang below the crankshaft, they're called inverted inline engines. These actually offer benefits like allowing for shorter landing gear and giving the pilot better visibility over the nose. Inline engines have a very narrow frontal area, which is great for streamlining the aircraft. Historically, though, larger air-cooled inline engines started having cooling problems as they got bigger, so they tended to be confined to lower to medium horsepower light aircraft back in the day.
Okay, inline. What else?
Then we have opposed or O-type engines. These are incredibly common in today's general aviation. Think of the typical Cessna or Piper. Here you have two banks of cylinders directly opposite each other, lying flat and sharing a single central crankshaft. They are almost exclusively air-cooled in aviation and usually mounted horizontally. Their big advantages are an excellent power-to-weight ratio and a very narrow, flat profile. This makes them perfect for fitting neatly into wings, especially in twin-engine aircraft. Pilots also tend to appreciate their inherent smoothness. They generally have low vibration levels.
Right, the flat engines you see on most small planes.
Exactly. The source material also briefly mentions V-type engines and radial engines, although our main focus here is inline and opposed based on the text. But radial engines, where cylinders are arranged in a circle around a central crankshaft, like spokes on a wheel, they have some interesting features. One key aspect is their propeller shaft, which is often splined for a strong connection, and they have a very robust thrust bearing. This bearing is specifically designed to absorb the immense forward pull, the thrust, generated by the propeller, and transfer that force effectively to the airframe without damaging the engine internals.
It's fascinating how the physical layout impacts so much. Now let's talk about quantifying these power plants. How do we measure an engine's basic size or potential? Terms like piston displacement and compression ratio come up a lot.
Yeah, these terms are crucial for understanding an engine's capacity and potential performance. Piston displacement essentially tells you the total volume of air that all the pistons sweep out in one complete stroke cycle. Think of it as the engine's breathing capacity in a single cycle. It's calculated based on the cylinder's bore, which is its diameter, and the stroke, which is the distance the piston travels. For example, the text gives a calculation where a single cylinder displaces about 1,479 cubic centimeters. So a four-cylinder engine built with those cylinders would have a total displacement of nearly 6,000 cubic centimeters, or about 5.9 liters. This number directly relates to how much fuel-air mixture the engine can process per cycle. So displacement is a fundamental indicator of potential power output.
Bigger displacement generally means more potential power, basically.
Generally, yes, all else being equal. The other critical measure is compression ratio. This is a comparison. You take the total volume inside the cylinder when the piston is at the very bottom, UDC, and compare it to the much smaller volume when the piston is at the very top, TDC. The higher the ratio, the more that fuel-air mixture gets squeezed before ignition, and the more you compress it, the more potent it becomes when ignited. So a higher compression ratio generally means more potential power. It's described as a controlling factor in maximum horsepower. However, there's always a limit. You can only push the compression so high based on the grade of fuel you're using. If you go too high, you risk dangerous pre-ignition or detonation, which can quickly destroy an engine.
So it's a balancing act between squeezing more power out and not blowing things up.
Precisely. It's always about managing those pressures and temperatures within safe limits for the materials and the fuel.
Okay, we've covered the fundamental principles of how they work. Now let's explore the actual physical architecture. What holds all these incredible moving parts together? The foundation and strength of the engine.
Right, that would be the engine block and crankcase. This isn't just a simple casing. It's the rigid backbone of the entire engine, designed to withstand immense forces and vibrations. Many crankcases are actually built in sections. This is a huge advantage for maintenance, really. You can often remove just one section for inspection or repair without disturbing the critical adjustments of the internal bearings, which simplifies overhaul procedures significantly.
Makes sense. And how does it attach to the plane itself?
The crankcase features these really robust mounting lugs. These are the specialized attachment points used to secure the entire engine assembly to the aircraft structure, the firewall or wing nacelle. These aren't just simple bolt holes. They're engineered with, as the text says, ample strength for rapid maneuvers or other loadings, ensuring the engine stays securely fixed even under extreme flight conditions or hard landings. Inside the crankcase, you'll also find the intake pipes or passages that deliver the fuel-air mixture to the cylinders. These often use slip joints to accommodate thermal expansion as the engine heats up and cools down. It's absolutely vital these joints are perfectly sealed. Even a tiny air leak here can cause problems, like making the engine idle too fast or worse, leading to a dangerously lean mixture at full throttle, which can cause detonation.
So the crankcase provides the structure, but then how does all that rapid up and down motion of the pistons actually get turned into the spinning motion that drives the propeller? That seems like mechanical wizardry.
It really is quite clever. That's the crucial job of the crankshaft. This is the component that converts the linear, reciprocating motion of the pistons and their connecting rods into the rotational motion needed to spin the propeller. Crankshafts are typically forged from incredibly strong steel alloys, like chromium, nickel, molybdenum steel, specifically chosen to handle the immense repeated stresses from combustion. They have these offset sections called cranks or throws where the connecting rods attach. And they have precisely machined surfaces called journals, where the crankshaft rides smoothly on bearings within the crankcase.
Are they solid steel all the way through?
Interestingly, no.
The crank pins, the journals where the connecting rods actually connect, are often hollow. This serves two purposes. It reduces the overall weight of the crankshaft, which is always a goal in aviation. And, very importantly, it provides internal passages for lubricating oil to flow through the crankshaft to various parts of the engine. On some older engine designs, these hollow crank pins even acted as sludge chambers. Centrifugal force would fling heavier contaminants in the oil to the outside of these hollow areas, trapping them away from the critical bearing surfaces. But with modern ashless dispersant oils, which do a much better job of keeping particles suspended in the oil itself, these sludge chambers aren't really needed anymore. You also have sturdy crank cheeks connecting the crank pins to the main journals, and these often incorporate counterweights. These counterweights are essential for balancing the entire rotating assembly, ensuring smooth operation and minimizing engine vibration.
Okay, so the crankshaft translates the motion, but the pistons are the actual workhorses, directly feeling the force of combustion. Let's delve into those key components. The pistons themselves, their pins, and the rings that seal them.
Absolutely. The pistons are typically machined from tough aluminum alloy forgings. They have to be strong, yet lightweight. Their tops, the piston crowns, can be flat, convex, or concave, sometimes even designed with specific recesses called valve reliefs to avoid physically hitting the valves when they open. Around the piston circumference are machined grooves that hold the piston rings. These rings are absolutely critical.
What exactly do they do? They seem so small but so important.
They have two main jobs. First, the compression rings, located closer to the top of the piston, create a tight gas seal against the cylinder wall. This prevents the high-pressure combustion gases from leaking past the piston, known as blow-by, ensuring that maximum power is transferred downward. Second, lower down on the piston, you have oil control rings. Their job is to scrape excess lubricating oil off the cylinder walls on the downstroke, leaving just a thin film for lubrication. This prevents too much oil from getting into the combustion chamber, where it would burn, cause carbon buildup, and increase oil consumption. And as we mentioned earlier, in two-stroke engines, because of the ports in the cylinder walls, the rings are uniquely pinned to prevent them from rotating.
Right, so they don't snag. What connects the piston to the rod that pushes the crankshaft?
That connection is made by the piston pin, often called a wrist pin. These pins are usually hollow tubes made from very hard, case-hardened steel alloys. In modern aircraft engines, they are typically the full-floating type. This means the pin isn't fixed. It's free to rotate within both the piston bosses and the small end bearing of the connecting rod. To prevent the hardened steel ends of the pin from scratching or scoring the softer cylinder walls as the piston moves, soft aluminum plugs are often inserted into the ends of the pin. These act as sacrificial, non-abrasive bumpers.
Clever. Okay, this brings us right to the heart of where combustion actually happens. The cylinders, cylinder heads, and valves.
Precisely. The cylinders form the combustion chambers themselves. In air-cooled engines, which are most common in general aviation, the cylinders are easily recognizable by their external cooling fins. These fins dramatically increase the surface area to help dissipate the intense heat of combustion into the passing airflow. Bolted securely to the top of each cylinder barrel is the cylinder head. The head contains the crucial valve seats. These are precisely angled rings, often 30 or 45 degrees, made of hardened material against which the valves seal tightly when closed. Sometimes, the intake and exhaust valve seats have a slightly different angle, maybe a half-degree difference, to create a very fine line of contact, which can actually enhance sealing under high pressure. The cylinder heads also contain the threaded holes for the spark plugs.
And the valves themselves, the intake and exhaust valves, they play such a critical role controlling everything that goes in and out. It's truly fascinating how they manage to survive such incredible, extreme conditions.
You're absolutely right. Valve construction is a real marvel of material science and engineering, given the intense heat, high pressures, and constant impact they endure, cycle after cycle. The faces of the valves, the part that seals against the seat, are often fortified with incredibly durable alloys like stellite or nichrome. These exotic materials are welded onto the valve head and then precisely ground. They offer exceptional resistance to high-temperature corrosion, the constant shock of closing, and general wear.
Is there anything special about the stems? They seem pretty simple.
Not always. Here's an incredible piece of engineering insight into managing heat. Some high-performance intake and especially exhaust valve stems are actually hollow and partially filled with liquid metallic sodium.
Sodium, like the stuff that explodes in water?
The very same, but sealed inside the valve stem. Sodium is an exceptional conductor of heat.
As the valve rapidly moves up and down, this liquid sodium gets sloshed around inside the hollow stem. It picks up immense heat from the super hot valve head, which is directly exposed to combustion, and efficiently carries it down the stem towards the cooler valve guide. From the guide, the heat can then dissipate into the cylinder head and ultimately out through the cooling fins. This ingenious internal cooling system can slash the valve's operating temperature by 300 to 400 degrees Fahrenheit, dramatically increasing its lifespan and preventing burning or warping.
That is seriously clever, but it sounds potentially hazardous if something goes wrong.
It is. And the source includes a critical safety note here. Under no circumstances should a sodium-filled valve be cut open or subjected to treatment that may cause it to rupture. Exposure of the sodium in these valves to the outside air results in fire or explosion with possible personal injury. It really underscores the precision and care needed when handling these specialized components.
Wow, okay. Definitely noted. So the valves are opening and closing with this split-second timing. How is that entire intricate sequence precisely orchestrated? How does the engine know exactly when to open and close these vital pathways?
That precise orchestration is the responsibility of the camshaft and valve train. The camshaft is a rotating shaft equipped with precisely shaped protrusions called lobes, one for each valve, or pair of valves. The exact shape of these lobes determines two critical things: the valve lift, how far the valve opens from its seat, and the valve duration, how long it stays open, measured in degrees of crankshaft rotation. Each lobe usually has a gentle slope, or ramp, portion at the beginning and end. This isn't for lift, it's to gently start the valve train moving and take up any slack, cushioning the mechanism and reducing shock and wear as the valve begins to open and close.
So the cam lobe pushes something.
Exactly. The valve train operates like a carefully designed chain reaction. The cam lobe pushes against a cam follower, sometimes called a lifter or tappet. In most overhead valve engines, this follower then pushes a long, thin push rod upwards. These push rods are typically hollow tubes, which makes them both light and strong enough to resist bending. The hollow center also ingeniously allows lubricating oil to pass up through them, oiling the upper valve train components in the cylinder head. The push rod then actuates a rocker arm, which is essentially a pivoting lever mounted on the cylinder head. One end of the rocker arm is pushed up by the push rod, causing the other end to press down on the tip of the valve stem, forcing the valve open against its spring pressure.
And what closes the valve?
Once the high point of the cam lobe rotates past the follower, strong valve springs coiled around the valve stem take over. They forcefully snap the valve shut against its seat and push the entire valve train mechanism, rocker arm, push rod, follower back down, keeping the follower in constant contact with the camshaft, ready for the next cycle. It's also worth noting the gearing. In a typical four-stroke engine, the camshaft gear is exactly twice the size of the crankshaft gear. This means the camshaft rotates at precisely half the speed of the crankshaft. This makes sense because each valve only needs to open and close once for every 2 complete revolutions of the crankshaft, one full four-stroke cycle. It's a beautiful example of mechanical synchronization.
Perfectly timed mechanical ballet. Okay, so we've got this intricate mechanical system running, but how does the engine get the right amount of fuel and air to actually make all that power? Let's start with the classic system, the float carburetor. How did that work and what were its inherent challenges?
Right. For many, many decades, the float carburetor was the primary fuel metering system for smaller general aviation aircraft and many amateur-built machines. Its design is based on fairly simple fluid dynamics principles, making it generally reliable for those applications. At its core, a float carburetor has a float bowl, which acts as a small reservoir for fuel. Inside this bowl, a flute connected to a needle valve maintains a consistent fuel level, much like the tank in a toilet cistern. From this bowl, fuel is drawn through various passages into the engine's intake airstream. The main system is the main discharge nozzle, usually located in a narrowed section of the air passage called a venturi, where airflow speeds up and pressure drops, sucking the fuel out. Mixture controls allow the pilot to adjust the fuel-to-air ratio. A common type is a manual mechanical blocker that adjusts fuel flow, with stops for full rich, maximum fuel for takeoff high power, and idle cutoff, no fuel, to shut the engine down.
And there's something about air mixing before it sprays out.
Yes, the air bleed system. This is crucial. It introduces small amounts of air into the liquid fuel before it reaches the discharge nozzle. This starts breaking the fuel up into finer particles, essentially reducing its viscosity and making it easier to atomize thoroughly as it sprays into the main airflow. This leads to better, more even combustion. For idle operation, when the main throttle valve is nearly closed, a separate idle jet and passage provides a small amount of fuel, and an idle mixture screw allows for fine-tuning this low-speed mixture.
Okay, seems straightforward enough, but you mentioned challenges.
Yes. Float carburetors, especially in aviation, have inherent limitations. Their primary weakness is susceptibility to carburetor ice. Ice can form inside the carburetor's throat, even when the outside air temperature is well above freezing. This happens because the evaporating fuel dramatically cools the air, often dropping the temperature below freezing point right where the fuel is introduced. If there's moisture in the air, it freezes onto the surfaces, restricting airflow and potentially causing significant power loss or even complete engine failure. It's most common at lower throttle settings or during descents.
That sounds pretty serious.
It can be. Another limitation is that they really need positive G-forces to work correctly. Sustained inverted flight or severe negative G maneuvers can disrupt the fuel level in the float bowl, causing either fuel starvation or flooding. And finally, because the fuel is introduced at a single point, there can sometimes be slight variations in the fuel-air mixture distribution reaching each individual cylinder, especially in engines with long intake runners. This can impact overall engine smoothness and efficiency.
Those limitations definitely sound significant, especially for larger, more powerful aircraft or those needing aerobatic capabilities. So it seems like pressure carburetors were developed as a direct answer to those specific challenges. What advantages did they bring?
Exactly. For larger engines, particularly the big multi-row radials or powerful V-type designs that consumed huge amounts of fuel, float carburetors just became impractical. Imagine trying to manage a float bowl big enough for an engine burning, say, 70 gallons of fuel per hour. It would be enormous and incredibly sensitive to attitude changes. Pressure carburetors were a major step forward. Instead of relying on a float bowl and venturi suction alone, they spray pressurized fuel directly into the engine's induction system. This significantly reduces the possibility of ice forming during the fuel metering process itself, as the fuel isn't evaporating and chilling the air in the same critical way. Crucially, they are largely, as the text says, indifferent to flight attitude. They function reliably whether the aircraft is right side up, inverted, or pulling Gs in maneuvers. This made them suitable for much more demanding flight envelopes, like military fighters. Fuel flow could also be much more precisely controlled and tailored to the engine's demands across different altitudes and power settings.
How do they work, broadly speaking?
Well, their core components typically include an air throttle body, which houses the main throttle valve controlling airflow, and a regulator. The regulator is really the brain of the system. It constantly works to maintain an equilibrium between the air metering forces, created by airflow, and the fuel metering forces, controlled by fuel pressure. It does this by managing pressure differentials across various internal chambers, often labeled A, B, C, D, E. There's also a fuel control unit, which incorporates the mixture control, and the discharge nozzle, which sprays the fuel into the airstream. Many systems, like the popular Bendix PS series carburetors, also featured an automatic mixture control, AMC. This typically used a sealed bellows assembly that reacted to changes in ambient air pressure, altitude, or the pressure delivered by a supercharger turbocharger. It would automatically adjust the fuel mixture, leaning it out at higher altitudes. These AMCs often had a fail-safe design, meaning if the bellows leaked or failed, the system would automatically revert to a full, rich mixture, preventing a dangerously lean condition that could damage the engine.
That's a huge leap in automation and precision. And building on that foundation, what about fuel injection systems? That sounds like the ultimate level of precision fuel delivery, going even beyond pressure carburetors.
Fuel injection systems do indeed represent the pinnacle of precise fuel delivery for piston engines. Instead of mixing fuel and air in a central carburetor or pressure carb, they deliver fuel directly to each cylinder, usually into the intake port just before the intake valve, or sometimes even directly into the cylinder itself. Direct fuel injection, though less common in traditional aircraft piston engines.
What are some common types found in aviation?
One widely used system is a Bendix RSA fuel injection. Similar in principle to pressure carbs, it uses a regulator to maintain that delicate balance between air metering forces and fuel metering forces. A key feature is the design of the fuel nozzles. Each nozzle is subjected to a carefully managed hierarchy of pressures. The highest pressure comes from the fuel inlet, supplied via a flow divider unit. Then there's an air bleed source, and finally the lowest pressure is the manifold pressure inside the intake runner. This precise pressure differential controls fuel flow. The air bleed is vital here. It mixes with the fuel within the nozzle body itself just before discharge. This ensures thorough atomization of the fuel as it sprays into the intake port, leading to more efficient and complete combustion. Like the pressure carb AMCs, the bellows assembly in the RSA system's mixture control is also designed to fail safe to a full rich condition if a leak occurs.
Okay, Bendix RSA. What about Continental engines? I hear their system is quite different.
Yes, continental fuel injection systems are unique, primarily because they do not use a venturi to measure airflow, which is how most other carbureted or injected systems determine how much fuel is needed. Instead, Continental systems meter fuel flow based primarily on engine RPM, the throttle position, and the mixture control valve position. It's an approach that actually echoes some very early engine designs from the Wright brothers era, interestingly enough, moving away from simple drip-type systems. A distinctive feature is the engine-driven fuel pump, which directs fuel to a swirl well. This is a clever chamber designed to use centrifugal force to separate out any fuel vapors that might have formed, especially when the fuel is hot, before they can enter the metering unit and cause issues like vapor lock. These vapors are then ejected back to the tank via a vapor return line. This system also uses an aneroid valve, typically located within the pump, which acts as an automatic altitude compensator by varying the high, unmetered fuel pressure supplied to the fuel control unit. The fuel air controller itself contains the throttle valve and the mixture control valve, often a distinctive cloverleaf shape. Another interesting aspect is that the unmetered fuel pressure before the mixture control runs significantly higher, maybe 2 to 4 times greater than the meter pressure going to the nozzles. This higher pressure acts as a sort of reserve, ensuring rapid fuel delivery for quick acceleration or when operating a constant speed propeller, which can demand sudden changes in fuel flow. And like the Bendix system, the nozzle pressures are critical. Highest fuel inlet pressure, then air bleed pressure, then lowest manifold pressure. It's also crucial that all cylinders have the exact same size nozzle. If one cylinder is running lean or rich, the problem isn't the nozzle size. It's likely an issue elsewhere, like an induction leak or a partially clogged nozzle.
Fascinating differences. And then we get to the absolute cutting edge, FADEC, full authority digital engine control. That sounds like a complete paradigm shift.
It truly is. FADEC represents a revolutionary approach to engine management. It integrates what used to be separate systems ignition and fuel delivery into one cohesive, digitally controlled unit. Essentially, it's a solid-state digital electronic ignition system combined with sequential port fuel injection. Remarkably, it often has only one primary moving part in the fuel system, the fuel injector valve itself, opening and closing rapidly. FAD continuously monitors a whole range of engine parameters in real time. Crankshaft speed, crankshaft position, knowing exactly where TDC is, manifold pressure, induction air temperature, CHT, EGT, you name it. Based on this constant stream of data, its microprocessor automatically calculates and adjusts both the ignition timing and the fuel mixture injection timing for optimal performance under all operating conditions. There are no traditional magnetos, no manual mixture control lever for the pilot to worry about FAD candles at all. This massively simplifies pilot workload, improves fuel efficiency, and optimizes performance.
So it's constantly thinking and adjusting.
Constantly. Being microprocessor-based, FADC provides incredibly precise control. It can even anticipate and prevent adverse power changes if a fault condition is detected. It's designed with redundancy, typically having a secondary power source it can switch to if the primary aircraft electrical power is lost, ensuring the engine keeps running. FADT systems also perform continuous self-diagnostics. They can detect problems within themselves or the sensors they monitor and alert the pilot through a dedicated Health Status Annunciator (HSA) panel in the cockpit. They are incredibly robust systems, built to withstand extreme storage temperatures, operate reliably in intense heat or cold, and endure high humidity. All the components, the electronic control units, ECUs, power sources, ignition switch, various sensors, and fuel injector coils are interconnected by a streamlined, low-voltage wiring harness. It's really a smarter, more integrated, and ultimately more reliable way to manage a piston engine.
It's incredible how that all integrates. And ultimately, all this complexity from float balls to FADC is focused on one critical thing: getting the right amount of fuel and air into the engine. That fuel-air mixture ratio is such a critical balance, isn't it? It absolutely is. Gasoline, fundamentally, can only burn efficiently when it's mixed with the right amount of air, or more specifically, the oxygen within the air. Remember, air itself is about 78% nitrogen, which is mostly inert in combustion, and only about 21% oxygen. The precise proportion of fuel to air, usually measured by weight, is paramount. This ratio directly controls the speed at which the flame front propagates across the combustion chamber and the peak temperature reached during combustion. Getting it wrong leads to inefficient burning, power loss, and potential engine damage. And this balance changes with altitude, right?
Critically so. As an aircraft climbs, the atmospheric pressure drops and the air becomes less dense. This means that for a fixed volume of air entering the engine cylinder, there's actually less oxygen by weight compared to sea level conditions. A naturally aspirated engine with a simple carburetor, which tends to meter fuel based on air volume, would therefore run progressively richer, too much fuel for the available air, as it climbs if no adjustment were made. This is precisely why mixture control is essential in aircraft engines. It allows the pilot, or FAEDC, to manually or automatically lean the mixture, reducing the fuel flow relative to the airflow at higher altitudes to maintain that ideal fuel-to-air ratio for efficient combustion and best performance. Interestingly, while you might hear pilots talk about slightly different settings for best power versus best economy, the source notes that the actual mixture requirements for both are approximately the same for efficient combustion.
What happens if things go wrong with combustion timing? You mentioned pre-ignition earlier.
Right, pre-ignition is a serious issue. This is when the fuel air charge ignites before the spark plug is actually timed to fire. It's uncontrolled ignition. It can have several causes. Sometimes it can be an electrical fault, like moisture or conductive carbon tracking inside the magnetos distributor, causing the high-voltage spark to jump to the wrong terminal or arc across surfaces, firing a plug at the wrong time. More commonly, and often more dangerously, it's caused by an incandescent spot, a hot spot, inside the cylinder itself. This could be deposits on the piston or spark plug, or perhaps an overheated, leaking exhaust valve edge glowing red hot. This hot spot acts like a glow plug, igniting the mixture prematurely during the compression stroke. Pre-ignition puts immense stress on engine components and can lead to rapid, severe engine damage because combustion is happening while the piston is still trying to move upwards.
Definitely something to avoid.
Well,
Okay, let's shift focus slightly. We understand the engine's internal dance now, but how does that precision hold up against the unpredictable forces of nature? What does the ambient environment, the air outside, actually mean for engine performance when you're flying?
The environment plays a huge role in how much power an engine can actually produce. There are three key atmospheric variables pilots and technicians always need to consider. First, ambient pressure, which is directly linked to altitude. The source gives a great example. Think about a standard, naturally aspirated, piston-powered aircraft taking off. At sea level, its rate of climb might be quite strong. But as it ascends 5,000 feet, 10,000 feet, 15,000 feet, that rate of climb will steadily diminish. Why? Because as you go higher, the air becomes rarefied or thinner. There are simply fewer air molecules, and critically, fewer oxygen molecules packed into each cubic foot of air. Since the engine essentially takes in a constant volume of air per cycle, it ends up ingesting less oxygen mass at higher altitudes. Less oxygen means less fuel can be burned efficiently, which directly translates to a reduction in the horsepower the engine can develop. Without some form of supercharging or turbocharging, most naturally aspirated piston engines will really struggle to climb much beyond 15,000 feet, if they can even reach it. Every aircraft has a service ceiling, a maximum practical altitude, and that's fundamentally limited by this decreasing ambient pressure.
Okay, so higher means thinner air, less power. What about temperature?
Second, temperature is a massive factor. We all know hot, humid summer days feel sluggish, and engines feel it too. Hot air is less dense than cold air. The source mentions a Cessna 150 example. On a hot day, its takeoff distance might increase by 10% for every 35 degrees ARA above the standard temperature, and its rate of climb could drop by 15 feet per minute for every 10 degrees ARA above standard. This goes back to basic physics, like Charles's law, which relates gas volume and temperature. Essentially, hotter air means the air molecules are moving faster and are spaced further apart. So again, for the same volume of air entering the cylinder, you get fewer oxygen molecules compared to colder, denser air. The simple rule is, as temperature goes up, engine performance goes down. Adding to that, higher intake air temperatures also tend to cause the fuel-air mixture to become richer, less dense air for the same fuel volume, which can further reduce power output slightly.
And the third factor is humidity. Does water in the air matter?
It does. Third, humidity also plays a role, particularly on those really muggy days. High humidity reduces engine performance because the air is already partially saturated with water vapor. Water vapor isn't oxygen. It displaces oxygen molecules. So when the engine draws in humid air, it's getting fewer oxygen molecules per intake stroke compared to drawing in dry air at the same temperature and pressure. Less oxygen available for combustion means less efficient burning and reduced power output. It's why, as the source humorously notes, when the temperature and humidity are high, humans become uncomfortable, and aircraft engines perform noticeably worse. Takeoff runs get longer, climb rates decrease.
So nature definitely presents some pretty significant limitations, especially for trying to fly high or operate in hot conditions. If we connect this to the bigger picture, how do engineers and aircraft designers overcome these atmospheric challenges? This sounds like the perfect job for supercharging and turbocharging.
That's precisely their purpose, to counteract the power loss caused by decreasing air density at altitude or high temperatures. They're forms of forced induction. Internally driven superchargers are one approach. These use a compressor, but it's driven mechanically directly by the engine's crankshaft, usually through a step-up gear train to achieve the necessary high compressor speeds. This compressor takes the incoming fuel-air mixture, or just air in some systems, and forces it into the cylinders at a pressure higher than ambient atmospheric pressure, effectively increasing the density of the charge and allowing the engine to produce more power, especially at altitude. In some supercharged fuel-injected engines, the fuel is delivered right into the throat of the compressor impeller for efficient mixing before compression.
And turbochargers, they seem more common now.
Yes, turbochargers are far more prevalent in modern high-performance piston aircraft. They are incredibly clever because they use energy that would otherwise be wasted, the heat and pressure energy in the engine's exhaust gases. The hot exhaust gas is directed to spin a turbine wheel. This turbine is connected via a shaft to a compressor wheel, which sucks in ambient air and compresses it before sending it to the engine's induction system. This compressed intake air is often called upper deck air. So the turbocharger essentially uses free energy from the exhaust to force more dense air into the engine, allowing it to maintain sea level power, or close to it, up to much higher altitudes, known as the engine's critical altitude.
What are the key parts of a turbo system?
A basic turbocharger system has three main components: the turbine section, the hot side, which extracts energy from the exhaust; the compressor section, the cold side, which compresses the intake air, increasing its density but also its temperature; and a robust central bearing and lubrication system to handle the extremely high rotational speeds, which can exceed 100,000 RPM. An absolutely critical component is the wastegate. This is essentially a bypass valve, usually a butterfly type, located in the exhaust system before the turbine. Its job is to control how much exhaust gas actually flows through the turbine versus how much bypasses it and goes straight out the exhaust pipe. By regulating the amount of exhaust energy reaching the turbine, the wastegate controls the turbocharger's speed and consequently the amount of boost pressure, upper deck pressure, delivered to the engine. It can be controlled manually by the pilot, but more commonly it's controlled automatically by systems using engine oil pressure acting against spring tension. A crucial safety feature is that wastegates are often designed to fail safe to the open position. This means if the control system fails, the wastegate opens, diverting most exhaust around the turbine, which significantly reduces boost pressure and prevents a potentially catastrophic engine overboosting scenario.
So there need to be controls to prevent too much boost.
Absolutely. Uncontrolled boost could easily destroy an engine. Turbocharging systems incorporate various controllers to safeguard against exceeding pressure or temperature limits, which could lead to detonation or other damage. For example, many systems use a density controller. This device senses the pressure at the compressor outlet, the upper deck pressure. If this pressure reaches the engine's predetermined maximum limit, the density controller signals the wastegate actuator, often by bleeding off control oil pressure, to open the wastegate further. This diverts more exhaust, slows the turbo down, and brings the upper deck pressure back within limits. It essentially wants to spin the turbine fast enough to produce maximum limit upper deck pressure all the time, but only up to the critical altitude. Above critical altitude, the wastegate will be fully closed, trying to get maximum possible boost from the thin air. Some systems also use a differential pressure controller. This provides more nuanced control by comparing the upper deck pressure to the actual engine manifold pressure. It adjusts the turbine speed to supply only the amount of upper deck pressure needed to achieve the desired manifold pressure set by the pilot's throttle, rather than always aiming for the maximum limit. This can reduce wear and tear on the turbocharger. And as an ultimate safety net, many turbocharged light-coming engines, for example, have an absolute pressure relief valve, similar to Cessna's manifold pressure relief valve. This valve is located in the induction system between the compressor outlet and the fuel metering unit. If, for some reason, the upper deck pressure exceeds its rated maximum value, say by about 2 inches of mercury, This valve will pop open and bleed off the excess pressure harmlessly into the engine compartment, preventing overboosting and potential damage to the induction system.
Okay, that makes sense. So we've covered how nature impacts performance and how engineers counteract it with forced induction. But what about factors that are more within the pilot's or technician's control, or common problems that can unexpectedly crop up and hurt performance?
Yes, there are definitely operational factors and common maintenance issues that can significantly degrade engine performance, even if the engine itself is fundamentally healthy. First, simple induction system issues. A classic example is the carburetor heat control cable failing to allow the heat valve to return fully to the full cold position after being used. If it's stuck partially open, the engine is constantly ingesting heated, less dense air. This enriches the mixture and reduces power output. A pilot would typically notice this during the pre-takeoff run-up check. The RPM won't return fully after checking the carb heat. Also, air leaks anywhere in the induction system downstream of the throttle valve, like a cracked intake hose or a poorly sealed slip joint, are bad news. They lean out the mixture, which can cause the engine to idle poorly or too fast, or much worse, lead to detonation and potential valve damage at high power settings.
What about the controls themselves?
Second, improper control rigging is a surprisingly common culprit for low power. If the throttle control cable isn't adjusted correctly, the throttle valve might not actually reach the full open position when the pilot firewalls the lever. Simple as that, you're not getting full power because you're not asking for it correctly. Similarly, for aircraft with controllable pitch propellers, if the propeller control isn't rigged properly to allow full travel into the high RPM low pitch takeoff position, the engine won't be able to reach its maximum rated takeoff RPM, resulting in reduced thrust. Third, exhaust system leaks can definitely rob power. These are quite common, especially around the exhaust port gaskets, where the manifold bolts to the cylinder head after many hours of heat cycles and vibration. Leaking exhaust gases mean less energy is available to drive a turbocharger if fitted, and even on naturally aspirated engines, leaks can disrupt exhaust scavenging and affect performance.
Internal engine adjustments matter too, right? Like valves.
Fourth, absolutely. Improperly adjusted valve clearances can have a significant adverse effect on power. If the clearance, the small gap in the valve train when the valve is closed and cold, is too large, the valve won't open as far or for as long as designed. If it's too small or zero with malfunctioning hydraulic lifters, the valve might not close fully, leading to leaks. Either way, restricted valve operation hinders the engine's ability to breathe efficiently, getting the fresh charge in and the burn gases out, directly reducing power output. This is especially critical with engines using zero-lash hydraulic lifters. If they fail, performance suffers. And finally, it's worth reiterating: pre-ignition and detonation. As we discussed under fuel mixtures, these uncontrolled combustion events are not just performance inhibitors. They are extremely dangerous and can cause catastrophic engine damage very quickly by putting immense thermal and mechanical stress on pistons, valves, and cylinders. Detecting and addressing the root cause is paramount.
Makes sense. Lots of potential pitfalls. Now, if we connect this to the bigger picture again, what's often overlooked but absolutely essential in keeping these powerful, hot, fast-moving machines running smoothly for potentially thousands of hours, it's not just about fuel, air, and sparks, is it? It's got to be about lubrication.
That's absolutely right. The lubrication system is truly the unsung hero of engine longevity and reliability. It performs far more critical roles than just making parts slippery. It's absolutely fundamental to the engine's health and efficient operation. Lubricants, typically engine oil, perform 5 core functions in an aircraft piston engine. First, and most obviously, reducing friction. Wherever parts move against each other, whether it's sliding friction in plane bearings, rolling friction in ball or roller bearings, or the wiping friction between gear teeth, lubricating oil forms a thin, protective film between the surfaces. This prevents direct metal-on-metal contact, which dramatically reduces wear, minimizes frictional heat generation, and prevents the power loss that friction would otherwise cause.
Okay, reduces friction.
Yeah.
What else?
Second, transferring heat for engine cooling. Oil is actually a remarkably efficient heat transfer medium. As it circulates throughout the hot engine core, it absorbs a tremendous amount of heat, particularly from the underside of the pistons and the cylinder walls, which are difficult to cool directly with air. The source notes that in a typical engine, only about a quarter of the fuel's energy actually becomes useful power. Roughly half goes out the exhaust pipe as waste heat, and the remaining quarter is absorbed by the engine structure itself. The circulating oil plays a vital role in carrying away a significant portion of this soaked-in heat, transporting it to the oil cooler if fitted, and the oil tank where it can be dissipated into the atmosphere. It's a critical part of the engine's overall thermal management system.
Wow, I didn't realize it did so much cooling.
It's a major secondary function. Third, cleaning the interior of the engine. Lubricating oil acts like the engine's bloodstream, actively cleaning internal components as it circulates. It picks up microscopic wear particles, combustion byproducts like carbon and soot, and any other foreign debris. It then carries these contaminants towards the oil filter, where they are hopefully trapped and removed from circulation. Modern aviation oils also contain special dispersant additives. These chemicals are designed to keep these tiny particles held in suspension within the oil itself, preventing them from clumping together to form sludge or varnish deposits that could clog narrow oil passages or cause abrasive wear. This is why used engine oil typically darkens over time. It's actually a sign the oil is doing its cleaning job effectively.
Okay, friction, cooling, cleaning. What else?
Fourth, serving as a hydraulic fluid. Because liquids like oil are practically incompressible, oil makes an excellent hydraulic fluid. This property is cleverly utilized in various engine components. For example, many engines use hydraulic valve lifters, which use engine oil pressure to automatically maintain zero valve clearance, reducing noise and wear. Propeller governors use precisely controlled oil pressure to change the pitch of propeller blades in constant-speed propeller systems. And the wastegate actuators in many turbocharger control systems also rely on modulated engine oil pressure to operate.
That's quite versatile. And the fifth function?
And finally, fifth, minimizing corrosion. When an engine is shut down and cools, moisture from the air can condense inside the crankcase and on internal parts. Oil provides a protective coating that helps prevent this moisture from causing rust and corrosion on vulnerable steel and aluminum surfaces. This is particularly important for aircraft that sit idle for extended periods. It's one reason why operating the engine regularly to get the oil hot to boil off moisture is recommended, or why special preservation oils, formulated to cling tenaciously to metal surfaces, are used when preparing an engine for long-term storage.
It really sounds like there's a whole science behind choosing the right type of oil. How has the performance of aviation engine oils evolved over the years? What different types are there?
Indeed. The selection and formulation of aviation lubricants are highly specialized fields. Petroleum lubricants, mineral oils derived from crude oil, are still the standard and most commonly used type in the majority of current aircraft piston engines. They're available in various viscosity grades. You can get straight-weight oils like SAE 50, where the viscosity is defined at a specific high temperature, or more common now are multi-viscosity grades, like 15W to 50. These use viscosity index improver additives to provide good flow characteristics when cold, the WO rating, while still maintaining adequate thickness and film strength when hot. This allows for easier starting in cold weather and better protection at high operating temperatures, often suitable for year-round use. Greases have very limited applications inside the engine itself, typically only used in specific low-speed, high-load areas requiring extremely high viscosity lubricant that will stay put, like certain magnetocam lobes or some older rocker arm lubrication points. Synthetic oils, manufactured through chemical synthesis rather than refined from crude oil, are also available for aviation use, either as pure synthetic formulations or as blends with petroleum oils. These often offer superior performance characteristics, particularly regarding thermal stability at very high temperatures and better flow properties at very low temperatures. But perhaps the most significant evolution in widespread use was the introduction of ashless dispersant, AD oils, over half a century ago. The ashless part refers to the type of additives used. They don't contain metallic elements that could form ash deposits in the combustion chamber. The dispersant part is key. Unlike older non-detergent oils that might allow contaminants to settle out as sludge, AD oils contain additives designed to keep microscopic particles, soot, wear metals, etc., suspended evenly throughout the oil. These suspended particles then either get trapped by the oil filter or are drained out along with the old oil during an oil change. As we noted, this is why AD oils tend to darken relatively quickly with use. It shows they are effectively cleaning the engine and holding on to the contaminants. It's important to remember, though, that AD oils are primarily designed to prevent new deposits from forming and keep new particles suspended. They generally won't remove significant pre-existing sludge or varnish buildup from an engine previously run on non-detergent oil.
That's a great insight into how the oil itself works chemically. But what about the specific physical characteristics that define an oil's effectiveness? It's not just about its type, right? There are properties like viscosity.
You're absolutely right. Several specific physical and chemical properties are critical to defining an oil's performance and suitability for a given engine and operating environment. Viscosity is arguably the most crucial property. It's technically defined as a fluid's internal resistance to flow. In simpler terms, a higher viscosity oil is thicker and flows more slowly, while a lower viscosity oil is thinner and flows more easily. Oil needs to be viscous enough at high operating temperatures to maintain a strong, protective lubricating film between moving parts under heavy load. But it also needs to be thin enough, when cold, to flow readily throughout the engine immediately upon startup, ensuring quick lubrication and minimizing cold start wear. Viscosity is typically measured using standardized tests, like with the Sable Universal Viscosimeter, and reported using grading systems like the SAE, Society of Automotive Engineers, grades.
Okay, viscosity is key. What else matters, especially for cold or hot conditions?
The pour point is very important for cold weather operations. It's the lowest temperature at which the oil will still flow or pour under specific test conditions. A lower pour point is obviously desirable for aircraft operating in cold climates, ensuring the oil remains fluid enough for the pump to pick it up and circulate it during engine startup. Related to this is the cloud point. This refers to the temperature at which any wax naturally present in a mineral oil begins to solidify and become visible, giving the oil a cloudy or hazy appearance. This temperature is usually slightly above the oil's actual solidification point, or pour point. Then, looking at high temperature characteristics, we have the flash point. This is the minimum temperature at which the oil gives off enough flammable vapors to form a combustible mixture with the air above its surface. This mixture will ignite momentarily flash if an external ignition source, like a spark or flame, is introduced. And closely related is the fire point. This is the temperature at which the oil vapors will not just slash, but will actually sustain continuous burning once ignited by an external source. Both flash point and fire point are important safety considerations in engine design and operation, indicating the oil's resistance to ignition at high temperatures.
Okay, that makes sense. Properties defining how it behaves hot and cold. Now, with the right oil chosen, how is it actually stored and circulated within the engine itself? I know there are two main system designs, wet sump versus dry sump. What's the difference?
That's right. The way the oil is stored and managed defines the two main types of lubrication systems. The wet sump system is generally simpler and more common in smaller, horizontally opposed general aviation engines, like the ubiquitous Continental O200 mentioned in the source. In this design, the engine's oil supply is stored directly within the engine's crankcase itself, specifically in the sump, which is the lowest part of the crankcase. The crankcase essentially acts as the oil reservoir or tank. The oil pump draws oil directly from this internal sump, circulates it through the engine, and the oil then drains back down into the sump by gravity.
And dry sump?
The dry sump system is typically used for larger, higher performance engines, especially radial engines, and some high-output opposed engines, particularly those that require significantly greater quantities of oil, making internal sump storage impractical or undesirable, for example, for aerobatics where oil sloshing is a concern. In dry sump system, the main oil supply is stored in a separate remote oil tank located somewhere else in the airframe or engine nacelle. The course mentions examples like a 9-cylinder radial needing 8 gallons, or a 14-cylinder radial needing 30 gallons, far too much to keep in the crankcase. There's still a small sump area at the bottom of the engine, but a dedicated high-capacity scavenge pump, often larger than the pressure pump, continuously draws the oil out of the engine sump as it returns from lubricating parts and pumps it back to the remote tank, frequently passing it through an oil cooler on the way. The main pressure pump then draws clean, cooled oil from this remote tank to circulate through the engine. Dry sump systems offer benefits like larger oil capacity, better cooling potential, and more consistent oil supply during maneuvers. An important design requirement for these remote oil tanks is that they must have adequate expansion space to accommodate the oil's thermal expansion as it heats up. Regulations typically require this space to be not less than the greater of 10% of the tank capacity, or 0.5 gallons, and, of course, the filler cap must provide an oil-tight seal.
Got it. Wet sump stores oil in the engine. Dry sump uses a separate tank. So how do we actually know the oil is doing its job effectively? And perhaps more importantly, how do we know if the engine itself is internally healthy? What tools and practices do technicians use to monitor the engine's health through its lubrication system?
That's a critical aspect of maintenance using the oil system as a window into the engine's condition. We rely on several key components and inspection practices. First, obviously, you have the oil pumps. There's the main pressure pump, usually a gear-type pump driven by the engine, that circulates the oil under pressure throughout the system to all the bearings, gears, and other lubricated parts. In dry sump systems, you also have the scavenge pumps returning oil to the tank. Then, crucially, you have oil filters. Their job is to remove harmful contaminants from the oil before it reaches sensitive engine components. Older engines might have simple screen filters or perhaps a Kuno filter,
a stack of cleanable discs. However, modern aircraft engines overwhelmingly use full-flow, disposable spin-on canister filters, much like those found on cars. These are typically positioned in the system after the pressure pump, but before the oil goes to the engine bearings, ensuring that all the oil being delivered is filtered. These spin-on filters contain pleated filter media inside a metal can. They also incorporate an anti-drain back valve to keep the filter full of oil when the engine stops, and importantly, a pressure relief valve or bypass valve. This valve is designed to open if the filter element becomes completely clogged, for example with cold, thick oil or excessive debris. If that happens, the bypass valve allows oil to flow around the filter element directly to the engine. This prevents oil starvation, which would be catastrophic, but it means the engine would temporarily be receiving unfiltered oil.
So inspecting that filter is really important.
Absolutely vital. A cornerstone of routine engine maintenance is the oil filter screen content inspection. For spin-on filters, technicians use a special cutting tool designed not to introduce metal filings from the cutting process itself to cleanly open the filter canister after it's removed during an oil change. They then carefully remove the pleated filter element and meticulously examine it, often washing it out over a clean surface, looking for any trapped metal particles or other debris. For older screen-type filters, the screen is simply removed, cleaned thoroughly, and inspected. Using a magnet helps quickly identify any ferrous, iron, or steel particles, which might indicate wear in components like cylinders, rings, or camshafts. Non-ferrous particles, like aluminum from pistons or casings, or bronze copper from bearings or bushings, are identified visually by their color and appearance. This inspection is considered absolutely fundamental, as the source emphasizes, regardless of any oil analyzing process like spectrometric oil analysis, SOA. Why? Because the filter captures larger particles, chips, flakes, chunks that might signal a more immediate or serious problem, like a failing bearing beginning to break up, which microscopic oil analysis focused on detecting minute wear trends over time might miss. The filter can also trap other foreign objects, like pieces of gasket material, or even occasionally bits of plastic ring left behind from an oil bottle.
Wow, okay. So filter inspection is key for finding bigger problems. What else?
Finally, many larger aircraft engines, radial engines, and especially helicopter transmissions incorporate chip detectors. These are essentially magnetic probes or plugs strategically placed in the oil sump or gearbox casing. Their purpose is to attract and capture any significant ferrous metal particles circulating in the oil, providing an early warning of potentially substantial internal wear or impending component failure, particularly in gear trains. These detectors are regularly removed, inspected for any accumulated metal fuzz or chips, and cleaned. Some advanced chip detectors even have a fuzz burning capability, where a small electrical current can be passed through the detector to burn off minor, harmless metallic dust, which might otherwise trigger a false warning, distinguishing it from larger, more significant chips indicative of a real problem. They provide a valuable real-time indication of trouble brewing inside.
Makes sense. Using magnetism to catch trouble early. Okay, we've covered how the engine runs, how it's lubricated, but before any of that can happen, the engine first has to start. Let's talk about ignition and starting systems. How are these powerful machines typically brought to life?
Right, starting methods have certainly evolved over aviation history. In the very early days, with relatively low-powered engines, starting was often a very manual process. Hand cranking or propping the propeller. Someone literally had to swing the prop by hand to turn the engine over fast enough to start. As you can imagine, this was physically demanding and could be quite dangerous. It was also especially challenging in cold weather, as the source notes, due to several factors. The reluctance of the primed fuel to vaporize properly in the cold, the inherently weak spark produced by early magneto systems at very low cranking speeds, and thick, congealed oil making the engine incredibly difficult to turn over.
Definitely sounds like a struggle. What's the modern approach?
Today, the vast majority of aircraft piston engines rely on an electric starter. These are typically powerful, series-wound DC electric motors specifically designed to produce very high starting torque, exactly what's needed to overcome the engine's internal friction and compression, especially when cold. This high torque is usually transmitted through a set of reduction gears to increase torque further, and then through an overload release clutch to prevent damage if the engine kicks back, to a starter drive mechanism. This mechanism, often a Bendix drive type with a pinion gear or a starter jaw, engages with a corresponding ring gear on the engine's flywheel, or a cranking jaw on the crankshaft accessory drive. Once the engine starts running under its own power and reaches a predetermined speed, the starter drive automatically disengages to prevent the engine from overspeeding the starter motor.
So electric starters are standard now, but even with them, cold weather can still be an issue.
Yes,
Despite modern electric starters, really cold weather starting can still be tricky. As mentioned, besides the issue of thick congealed oil increasing drag, the liquid fuel that's primed into the cylinders can be reluctant to atomize or vaporize properly in very cold temperatures. Liquid fuel doesn't burn well. You need fuel vapor mixed with air. This difficulty in getting a readily ignitable mixture, combined sometimes with a slightly weaker spark from the magnetos at slow cranking speeds, often necessitates the use of specialized starting aids or procedures in freezing conditions.
Okay, so the starter provides the spin. But beyond that mechanical rotation, how do we actually get that all-important spark to ignite the fuel? That's where the magneto system comes in, right? Generating its own electricity for ignition, independent of the battery once running.
Exactly. Magneto systems are truly remarkable pieces of engineering, primarily because they are self-contained ignition units. They use permanent magnets and rotating coils to generate their own high-voltage electrical current for the spark plugs. This means, crucially, that they don't rely on the aircraft's battery or electrical system to produce spark once the engine is running, a major safety advantage. If the aircraft loses all electrical power, the engine driven by magnetos will keep running. The most widely used type in general aviation is the high-tension magneto system. As the name implies, the system generates a very high voltage, potentially up to 20,000 volts or even more, right within the magneto unit itself. This high voltage, high tension, is then immediately directed through a distributor mechanism, also usually inside the magneto, to the correct spark plug via high-tension ignition leads. Early high-tension systems did face some challenges, particularly with high-voltage electricity tending to leak or flash over insulating surfaces at high altitudes where the air is thinner and less insulating. However, advancements in insulating materials and ignition harness shielding have largely overcome these issues in modern designs.
Was there an alternative developed?
Yes, specifically to address those early high-voltage leakage problems, especially in very high-altitude aircraft or aircraft equipped with extensive radio communication and navigation equipment that required thorough ignition shielding to prevent interference, the low-tension magneto system was developed. The clever idea here is that the magneto itself only generates a relatively low voltage. This low-voltage current is then distributed through shielded wires to a small transformer coil located right next to each individual spark plug. This local transformer then steps the voltage up to the very high level needed to jump the spark plug gap. By keeping the high voltage confined to a very short distance, just from the transformer coil to the plug, this design virtually eliminates the potential for high-voltage flashover within the main distributor block or along the length of the ignition harness. It provides excellent ignition performance, especially under demanding conditions.
Interesting approach. So digging inside a typical high-tension magneto, how does it actually generate and deliver that precisely timed high-voltage spark? What are the key internal components doing?
Okay, let's look inside a typical magneto. At the heart of the spark generation timing are the breaker contact points. These are a small set of electrical contacts, typically made from durable alloys like tungsten or platinum iridium, to resist the intense heat and electrical arcing they endure. They are opened mechanically by a cam driven by the magneto's rotating shaft. This opening occurs at a very precise moment in the engine's cycle, synchronized with piston position, often referred to as the E-gap, efficiency gap, position of the magneto's rotating magnet. This precisely timed opening of the points interrupts the flow of current in the magneto's primary circuit, which is the trigger event that generates the spark. The pivotless type is common now, reducing wear.
What's the condenser for? Always wired across the points.
The condenser, or capacitor, connected across the breaker points plays a crucial dual role. When the points snap open, the collapsing magnetic field in the primary coil tries to induce a very high voltage back into the primary circuit itself. The condenser absorbs this high self-induced voltage surge. This prevents the voltage from becoming high enough to arc across the opening points, which would cause them to burn and pit rapidly. By preventing this arcing, the condenser ensures the primary current stops flowing very abruptly. This rapid cessation of primary current flow is essential for causing a fast collapse of the magnetic field, which in turn is necessary to induce the maximum possible high voltage in the secondary coil. So it protects the points. AD ensures a strong spark. The coil itself is essentially an electrical transformer housed within the magneto. It has two windings wrapped around a soft iron core. The primary winding consists of relatively few turns of heavy copper wire. The secondary winding consists of many thousands of turns of very fine copper wire, heavily insulated. When the breaker points are closed, current from the magneto's generating circuit flows through the primary winding, building up a strong magnetic field in the iron core. When the points open, this primary current is interrupted, causing the magnetic field to collapse rapidly. As this collapsing magnetic field cuts across the thousands of turns in the secondary winding, it induces an extremely high voltage. Due to the high turns ratio, the voltage needed to jump the spark plug gap.
Okay, so points open, field collapses, high voltage is made. How does it get to the right spark plug?
That's the job of the distributor. Once that high voltage pulse is generated in the secondary coil, it needs to be directed to the correct cylinder spark plug according to the engine's firing order. The distributor typically consists of a rotating part, often called the rotor finger, which is geared to the magneto shaft, and a stationary distributor block, or cap. Both are made of high-quality non-conducting material. The block has embedded metal terminals, one for each spark plug lead, arranged in a circle. The spinning rotor finger passes very close to each terminal in sequence, allowing the high voltage to jump the tiny air gap from the rotor tip to the terminal, sending the spark down the correct ignition lead to the spark plug.
And the spark plug is the end of the line.
The spark plug is the final, critical component in the ignition journey. It's essentially a carefully engineered device that provides an air gap inside the combustion chamber for the high-voltage electricity to jump across. It has a central electrode insulated from the outer metal shell, which grounds to the engine. The high voltage from the magneto travels down the central electrode and arcs across the gap to the ground, electrode welded to the shell. This high-energy arc is the spark that ignites the compressed fuel-air mixture. The source poses a rhetorical question highlighting the extreme conditions. The device within a reciprocating engine must reliably function 17 times per second at a temperature of 3,000 degrees air-half, a gas pressure of 2,000 psi, and an electrical pressure of 20,000 volts. The answer, of course, is the spark plug. It's truly a marvel of engineering to withstand that environment repeatedly.
That really puts the demand on a spark plug into perspective. So given those challenges, especially during starting when the engine is turning slowly and maybe it's cold, what special aids are used to help ensure that spark reliably fires when the engine is just coming to life?
That's where dedicated starting aids come into play. They are designed specifically to provide a much hotter, more intense spark during the low RPM starting sequence than the magneto might produce on its own. One common type is the booster coil or induction vibrator. This is an external device, often powered by the aircraft battery just during starting. It uses a set of vibrating contacts, similar to an old-fashioned electric bell, to rapidly interrupt DC current flowing through the primary winding of a small coil. This creates a pulsating magnetic field, which induces a continuous series of high-voltage starts in the secondary winding. This output is typically fed into the magneto's distributor, bypassing the magneto's own coil and points, to provide a shower of sparks to the spark plugs during cranking, making starting much easier, especially in cold conditions.
Okay, a shower of sparks. What about the impulse coupling? I hear clicking during shutdown sometimes.
Right, the impulse coupling is another very common starting aid, particularly found on many horizontally opposed engines used in general aviation. It's a purely mechanical device built into the drive coupling of one, or sometimes both, magnetos. Its purpose is to give the magneto's internal rotating magnet shaft a brief acceleration, a sudden, quick flick or snap right at the moment the spark is needed during the slow engine cranking sequence. It does this using a combination of a cam, flyweights, and a coiled spring. As the engine turns slowly, the spring winds up, and then, triggered by the cam hitting stop pins, it suddenly releases, spinning the magneto magnet rapidly over a short distance. This rapid rotation generates a much hotter, more intense spark than would normally occur at slow cranking speeds. Impulse couplings are generally effective, but they can sometimes cause issues. The source mentions problems like magnetized flyweights, preventing proper engagement-disengagement, or thick congealed oil in very cold weather, preventing the flyweights from properly engaging the stop pins, leading to hard starting. A potential disadvantage compared to a booster system is that a standard impulse coupling typically provides only one strong spark per firing cycle during starting, not a continuous shower. That clicking sound you hear during shutdown is the impulse coupling flyweights retracting as the engine speed drops below the coupling's engagement RPM. It's a normal sound indicating it's likely working correctly.
And what about that LaSAR system you mentioned earlier with FADC? Does that help with starting too?
Yes, absolutely. Modern electronic ignition systems like LaSAR, Limited Authority Spark Advance Regulator, which bridge the gap towards full FADC, offer significant starting advantages. They inherently produce a much hotter, more consistent spark, even at very low cranking RPMs, because they aren't relying on the slow rotation of a magnet past a coil. Crucially, LaSAR often delivers a spark to every spark plug during the start sequence, maximizing the chances of ignition.
And its timing isn't fixed. It can be precisely controlled based on crankshaft position sensors and manifold pressure, providing the optimal spark timing for starting, which might be different from the timing needed once the engine is running. This typically results in quicker, more reliable starts, cleaner spark plugs over time due to more complete combustion, and reduced carbon and lead deposits. It really rivals modern automotive ignition performance.
Okay, one last point on ignition systems, battling moisture. You mentioned flashover. How do magnetos deal with condensation?
Moisture is indeed a major enemy for high-voltage ignition systems like magnetos. As the source explains, the rapid temperature changes an engine and its accessories experienced during operation and shutdown inevitably lead to condensation forming inside sealed units like magnetos and distributors. Since water is an electrical conductor, even a thin film of moisture on insulating surfaces can create a path for the high-voltage electricity to arc across the ground, or worse, jump to the wrong distributor terminal, sending the spark to the wrong cylinder at the wrong time. This is called flashover, and it can cause engine misfiring, rough running, and potentially even destructive pre-ignition.
So how is it managed?
Several strategies are used. Internal insulating components are often coated with special waxes or varnishes designed to make moisture bead up, rather than form a continuous conductive film. Additionally, most magnetos and distributors incorporate small vents. These allow a controlled amount of air to circulate through the unit as temperatures change, helping to carry away moisture vapor and keep the interior relatively dry. It's critical that these vents don't become obstructed by dirt or paint. It's also vital that the air circulating through the ignition system is kept free of oil contamination, perhaps from a leaking engine seal near the magneto drive. Even tiny amounts of oil vapor deposited on internal insulating surfaces can break down under high voltage, leading to flashover and a phenomenon called carbon tracking. This is where the electric spark literally burns the oil residue, creating fine pencil-like lines of carbon deposit. Carbon is conductive, so these tracks create a permanent pathway for the spark to follow, short-circuiting the intended path to the spark plug and causing persistent misfiring. Oil weeping from a magneto vent is often a sign of a leaking drive seal, requiring prompt attention.
Right, keep it clean and dry inside. Okay, this is great. We understand the engine, its fuel, its spark. Now let's connect this to the practical side. How do pilots and technicians actually know what's happening inside that complex machine while it's operating or being tested on the ground? What's the engine's voice? And how do they interpret its whispers and shouts through the instrumentation?
That's a crucial link understanding the engine's instrumentation. These gauges are the primary way the engine communicates its status to the flight crew and maintenance personnel. It's absolutely critical, as the source emphasizes, for pilots and technicians to remember that these gauges primarily report quantities, pressure, temperature, speed. They don't directly tell you the cause of an abnormal reading. However, if there is a problem, it will very often manifest itself as an abnormal reading on more than one gauge simultaneously. Correlating these readings is key to diagnosing issues.
Okay, so let's run through some of the most important gauges. What does each one tell us?
All right, let's start with the basics. The tachometer, or TACH, simply indicates engine speed in revolutions per minute, RPM. It usually has color-coded arcs on its face. A green arc indicating the normal continuous operating range, a red line for the maximum permissible RPM, which should never be exceeded, and sometimes a yellow arc indicating a range where operation is permitted but usually time-limited, like for takeoff power. Gaps in the green arc might also indicate ranges to avoid due to potential vibrations. Then there's the manifold absolute pressure, MAP gauge, found on engines with constant speed propellers or supercharging. This gauge measures the absolute pressure, not gauge pressure relative to ambient, inside the engine's induction manifold, typically in inches of mercury, OHG. MAP is a direct indication of the power the engine is being asked to develop. It's affected by the throttle position. Opening the throttle increases MAP. Engine RPM, increasing RPM generally increases MAP for a fixed throttle setting, as the pistons draw air in faster. And the ambient atmospheric pressure, which sets the upper limit for MAP in naturally aspirated engines.
Some MAP gauges also have color codings. Perhaps a blue arc indicating a typical range for operating with a leaned mixture for best economy crews.
Okay, RPM and power indication. What about temperature, EGT and CHT?
Yes. Temperature monitoring is vital. The exhaust gas temperature EGT gauge measures the temperature of the exhaust gases, usually via a thermocouple probe placed in the exhaust manifold or individual stacks. EGT is a very sensitive and quick-responding indicator of the combustion process. It's the primary tool pilots use for manual leaning the fuel air mixture in flight. As you lean the mixture from full rich, EGT increases until it reaches a peak value at the stoichiometric or chemically ideal mixture. And then it starts to decrease again if you continue leaning into the lean of peak region. The source mentions a common leaning technique involves leaning until EGT peaks, then enriching slightly until it drops by a specific amount, maybe 100 degrees half, for best power or economy, depending on the engine and pilot preference. Modern systems often have probes on each cylinder for more precise monitoring. The cylinder head temperature, CHT gauge, measures the actual temperature of the engine's cylinder heads, usually via a probe placed under a spark plug gasket or in a dedicated well in the cylinder head casting. CHT responds much more slowly to changes than EGT because it's measuring the temperature of a large mass of metal, not hot gas. It's a critical indicator of overall engine cooling effectiveness and helps warn against overheating conditions that could lead to detonation or engine damage. Like tachometers, CHT gauges have operating ranges and red lines. Multi-probe CHT systems are becoming more common, allowing monitoring of individual cylinder temperatures.
Oil gauges must be critical too.
Absolutely critical. The oil pressure gauge monitors the pressure being supplied by the engine's oil pump. This pressure is vital for ensuring proper lubrication and also contributes significantly to engine cooling. The source highlights a crucial safety rule. If there is no oil pressure within 30 seconds after starting, 1 minute for winter operation, abort the start. Loss of oil pressure in flight requires immediate action. Low pressure could indicate dangerously low oil quantity, oil that's too hot and thin, a failing pump, or a stuck pressure relief valve. High pressure might indicate cold, thick oil, normal on startup should decrease as it warms, or a malfunctioning relief valve. Fluctuating pressure often points to air trapped in the oil lines, very low oil quantity allowing the pump pickup to be uncovered, or a faulty pressure regulator. The oil temperature gauge displays the temperature of the oil, usually measured where it enters or leaves the engine or in the tank sump. Maintaining the correct oil temperature is important not just for proper viscosity and lubrication, but also, as mentioned earlier, for evaporating harmful moisture that accumulates in the crankcase. The source suggests oil needs to reach at least 180 degrees AVSAF for about 30 minutes during flight to effectively purge this water, preventing internal corrosion, especially in engines that aren't flown frequently. Consistently cool oil temps can be detrimental in the long run due to water buildup.
What about fuel monitoring?
Yes, fuel pressure gauge. Monitor the pressure within the fuel system. Simple gravity-fed systems might not have one, but systems with engine-driven pumps and/or electric boost pumps rely on maintaining pressure within the specified green arc range for proper fuel delivery to the carburetor or fuel injection system. The gauge typically measures pressure at the inlet to the carburetor or fuel control unit. Low fuel pressure is a serious issue. For aircraft equipped with continuous flow fuel injection systems, a fuel flow meter is common. This gauge measures the rate at which fuel is being consumed, typically displayed in gallons per hour, GPH, or pounds per hour, pph. It's another valuable tool for setting power precisely and managing fuel reserves. The accuracy of these meters depends heavily on the correct placement of the flow sensor, transducer, within the fuel system, after the throttle valves but before the manifold valve in a continental system.
And electrical system health.
Right. You also have basic electrical gauges. An ammeter shows the rate of current flowing into or out of the battery, charge-discharge. A voltmeter shows the overall electrical system voltage, indicating whether the generator or alternator is operating correctly, typically around 14 or 28 volts. Some aircraft use a load meter instead of, or in addition to an ammeter, showing the total electrical load being drawn from the altergenerator. A simple discharge light might illuminate if the battery is discharging, indicating a charging system failure. Monitoring these helps ensure the health of the aircraft's electrical system, which powers starters, lights, radios, instruments, and sometimes FADC systems. There's usually an hour meter, like the Hobbs meter, that records the total time the engine has been operating. It's often activated automatically by an oil pressure switch, so it only runs when the engine is running. This is crucial for tracking maintenance intervals. And finally, as aircraft instrumentation becomes more digitized, we see multifunction displays, MFDs, becoming increasingly common, especially in newer aircraft or those with upgraded glass cockpits.
These large LCD screens can display information from multiple engine sensors simultaneously, often in graphical formats like dials or bar graphs. They make very efficient use of limited panel space, can be programmed with checklists and warning systems, and provide pilots with a much more comprehensive integrated view of engine health and performance at a glance.
That's a lot of information the engine is providing. Knowing how to read those gauges is clearly vital. But let's back up to the very beginning of an operation. What are the absolutely essential steps before you even think about turning the key and coaxing that engine to life during the pre-start and starting phases?
Absolutely. Before any engine operation, a thorough and systematic pre-start inspection is non-negotiable for safety. This involves more than just kicking the tires. You need to visually check for any signs of fuel, oil, or hydraulic fluid leaks under the engine cowling and around the aircraft. Verify fuel and oil quantities are adequate for the intended flight, and check fuel samples for water or other contamination. Ensure the propeller is clear of obstructions and appears undamaged. Confirm brakes are holding or wheel chocks are securely in place. If possible, position the aircraft facing into the wind for better cooling during ground operations. And, especially if starting in a confined area or hangar, have appropriate fire guard equipment, like a fire extinguisher, readily accessible.
Okay, check's done. What about the actual starting procedure? Does it vary much?
The specific starting procedures can vary slightly depending on the exact engine and fuel system, so the manufacturer's Pilot Operating Handbook, PO8, or Aircraft Flight Manual, AFM, is always the definitive guide. However, the general steps are similar. For a typical carbureted engine, first, ensure the fuel selector valve is on, supplying fuel to the engine. Crack the throttle open slightly, maybe 14-inch. Set the mixture control lever to full rich. If equipped with a controllable pitch propeller, set the prop control to full increase RPM, low pitch high RPM setting. Turn the master switch on, then turn the magneto switch to both. Before engaging the starter, loudly announce clear prop to warn anyone nearby. Engage the starter. Once the engine catches and starts running, immediately check the oil pressure gauge and adjust the throttle to the recommended warm-up RPM for a typical fuel-injected engine. The procedure is similar, but with a couple of key differences related to the fuel system. You'll also turn the electric boost pump on if required for starting. A significant difference is often the mixture control position during the actual cranking. For many injected engines, you start with the mixture control in the ideal keyed-off position. You crank the engine, and only after it fires and starts to run do you smoothly move the mixture control forward to the full RICH position. This helps prevent overpriming or flooding the engine during start.
What about problems like vapor lock during start?
Yes, vapor lock can be a nuisance, especially when trying to restart a hot fuel-injected engine, or sometimes at high-altitude airports on hot days. This occurs when fuel in the lines gets hot enough to boil and turn into vapor instead of liquid. Fuel pumps are designed to pump liquid, not vapor, so this interrupts fuel flow. Procedures for clearing vapor lock vary. The goal is usually to either cool the fuel lines down or use the boost pump pressure to force liquid fuel through and purge the vapor. For example, the source described a typical procedure for a Continental injected engine might involve setting the throttle full open, mixture to idle low cutoff, and running the boost pump for about 30 seconds to flush the vapor back to the tank, then attempting a normal start. RSA systems might require protracted priming. Methods to convert vapor back to liquid fundamentally involve cooling the fuel, increasing its pressure, or both.
Okay, so the engine's running, you've taxied out, maybe even taken off, but the diagnostics don't stop there. What are the crucial checks done after starting, like during the run-up before takeoff, and how do you use that instrument data to troubleshoot potential issues?
Right. The run-up checks before takeoff are critical for verifying the engine, and its systems are operating correctly before committing to flight. And interpreting the gauge readings during these checks is key, once the engine is running and warmed up slightly. First, as we stressed, an immediate confirmation of positive oil pressure after start is vital. During the run-up, you reconfirm it's within the normal operating range, the green arc. Similarly, fuel pressure must be verified within its green arc. You'll also check the generator alternator system is working correctly by observing the ammeter voltmeter readings, ensuring the battery is charging or system voltage is stable. An absolutely critical diagnostic performed during the run-up is the magneto drop check. This is done at a specific RPM recommended by the manufacturer, for example, 1700 RPM. The pilot switches the magneto key from the both position momentarily to left only, then back to both, then momentarily to right only, and back to both. While operating on a single magneto, you watch the tachometer for an RPM drop. A small, smooth drop, typically 5150 RPM, check the TOH for exact limits, is normal and expected, indicating that both magnetos are functioning correctly. An excessive RPM drop, for example over 150 RPM, or a very rough running engine during the drop indicates a problem with the opposite magneto system, fouled plugs, bad lead, etc. The source makes an interesting point. A 50 RPM drop on the left magneto might indicate a serious defect in the right magneto. Why? Because if the right magneto system is barely contributing, the engine is running mostly on the left one already. When you switch to left only, the RPM drop is small because the faulty right side wasn't doing much anyway. You'll also notice that manifold pressure increases slightly during a magneto drop. This is normal. As the RPM decreases due to running on one mag, the engine takes fewer intake strokes per minute, leading to less airflow demand for the same throttle setting, thus increasing the pressure measured in the manifold.
Okay, mag check is crucial. What about carb heat?
Next is the carburetor heat alternate air check, or carbureted some injected engines. When carb heat is applied, you should normally see a slight RPM reduction, maybe 50-75 RPM. This is because the heated air entering the carburetor is less dense, which enriches the fuel air mixture slightly, causing a small power loss. If you see an RPM gain when applying carb heat, it could indicate that the main air filter or air intake path is partially blocked, so the engine prefers the alternate heated air source, or possibly that the mixture was excessively lean to begin with. It's also important to remember that carb heat often supplies unfiltered air, and if there's an exhaust leak nearby, it could potentially draw exhaust fumes into the engine cabin. For aircraft with controllable pitch propellers, propeller checks are performed during the run-up. This involves cycling the propeller control lever to check that the propeller governor is operating correctly, changing blade pitch to maintain or change RPM as commanded, and, if equipped, testing the feathering system, which drives the blades to a high-pitch, low-drag position. You'll observe changes in RPM and manifold pressure during these checks.
How do you generally interpret overall performance during run-up?
When interpreting overall engine performance, you're basically comparing power input, throttle setting, indicated by MAP, versus power output, indicated by RPM. The source notes a higher than normal manifold pressure indicates that the engine is performing poorly if the RPM achieved at that MAP is lower than expected. This suggests the engine isn't efficiently converting the fuel air charge into rotational speed, implying you need more throttle, higher MAP, just to get the same output. You also monitor the engine response to power changes smoothly. Advancing and retarding the throttle should result in smooth, immediate engine response without hesitation or stumbling. A crucial safety check, usually performed just before shutdown at idle RPM, is the magneto switch ground-out check. Briefly switching the magneto key to the all-off position should cause the engine to immediately quit, or stumble significantly. Then quickly switch back to both to keep it running. This verifies that the P-leads, the grounding wires from the magnetos to the switch, are intact, and the all-off position actually does ground the magnetos, preventing accidental engine start if the propeller is moved later. This check is never performed at high RPM, as dumping unburned fuel into a hot exhaust system when the ignition cuts out can cause damaging backfires or loud explosion sounds. Finally, one last check often done during engine shutdown is listening for the impulse coupling, if equipped. As the engine spools down through the lower RPM range, you should hear a series of distinct, consistent clacking sounds as the impulse coupling flyweights engage and disengage. If the clacking sounds intermittent, weak, or absent, it could indicate a worn coupling mechanism, sticking flyweights, perhaps due to magnetism or cold oil, or worn stop pins, potentially leading to hard starting problems later.
That's a comprehensive set of checks. Now, beyond the cockpit gauges and run-up procedures, what deeper diagnostic tools do technicians use to really look inside the engine without having to completely tear it apart? How do they get a true internal picture of engine health?
These non-invasive diagnostic tools are incredibly valuable for proactive maintenance, troubleshooting hidden issues, and assessing the overall condition of the engine's core components. Compression tests are absolutely fundamental for evaluating the health of the cylinder specifically, how well the piston rings, valves, and cylinder itself are sealing. There are two main types. The differential compression test is perhaps the most popular and informative method for propeller-equipped aircraft engines. It requires a source of compressed air, typically regulated to 80 psi for the test, and a special gauge set with two pressure gauges and a restricting orifice between them. The technician carefully rotates the engine crankshaft to position the piston in the cylinder, being tested precisely at top dead center on its compression stroke, TDCC. Compressed air is then fed into the cylinder through a spark plug hole adapter. The first gauge shows the input pressure, 80 psi, and the second gauge shows the pressure actually being held inside the cylinder. The difference indicates the amount of leakage. A reading like 75/80, 75/80, means the cylinder is holding 75 psi with 80 psi applied, indicating relatively low leakage and good sealing. Readings below a certain threshold, for example 60/80, usually warrant further investigation. The beauty of the differential test is that while the air pressure is applied, the technician can listen for where the air is escaping. Hissing sounds coming from the intake suggest a leaking intake valve. Hissing from the exhaust pipe points to a leaking exhaust valve. Hissing from the crankcase breather indicates worn or broken piston rings, allowing air past the piston. And hissing from an adjacent cylinder spark plug hole could mean a leaking head gasket or even a cracked cylinder wall. Precise piston positioning at TDCC is critical for accurate and safe results. The direct compression test is simpler, much like the compression test done on automotive engines. It uses a single gauge that measures the peak pressure developed inside the cylinder during cranking with the starter motor.
It doesn't require an external compressed air source or precise crankshaft positioning. However, it's generally considered less informative than the differential test because it doesn't easily allow the technician to pinpoint the source of any leakage. No hissing sounds to follow. Its main value is in comparing the peak pressures between cylinders. A cylinder reading significantly lower than the others indicates a problem.
What about actually seeing inside?
For that, we have the borescope. This has become an indispensable tool in modern aviation maintenance. It's essentially a small optical probe, either rigid or flexible, often with its own light source and sometimes a camera, that can be inserted through a spark plug hole. It allows the technician to perform a direct visual inspection of normally hidden areas inside the cylinder, such as the valve faces and seats, looking for burning, pitting, or cracking, the piston crown, looking for carbon buildup or damage, and the cylinder walls, looking for scoring, corrosion, or wear patterns. The source rightly states that borescopes can greatly increase aviation safety and reduce maintenance costs by allowing early detection of problems without requiring costly and time-consuming engine disassembly. Borescope inspections are often performed in conjunction with compression tests. One manufacturer even recommends it specifically alongside their compression test procedures. And we must reiterate the importance of the oil filter screen content inspection. As the source says, normal visual inspections of filters and screens are fundamental, regardless of any oil analyzing process. It's the best way to find those potentially critical larger metal particles, pieces of gasket, or other foreign objects that microscopic oil analysis might miss, providing immediate, tangible evidence of the engine's internal condition. Finally, for engines specifically equipped with them, like Rotax 914 or Bureau engines mentioned later, regular magnetic plug inspection is crucial. These plugs, located in the crankcase or gearbox, are removed and checked for accumulated metal chips or fuzz. This gives a direct indication of wear occurring within the gearbox or engine internals. While small amounts of very fine steel fuzz might be considered normal, finding significant chips requires investigation and potentially repair or overhaul.
Okay, that covers looking inside. Let's zoom out again to the whole engine installation. From the big picture, that engine cowling isn't just about making the plane look sleek and pretty, is it? It seems to serve some really critical functions.
Absolutely. The engine cowling is far more than just aerodynamic fairing, although that is one of its important functions, streamlining the bulky engine to reduce drag. But perhaps its most critical role is in engine cooling, especially for air-cooled engines. The cowling is carefully designed, working in conjunction with internal baffles and seals, to precisely direct the flow of cooling air over the hot cylinder heads and barrels. It creates a high-pressure area in front of the engine and a low-pressure area behind it, forcing air through the cooling fins. If the cowling is damaged, ill-fitting, or if the flexible baffle seals are torn, missing, or improperly positioned, the cooling airflow can be disrupted, leading to ineffective cooling and potentially dangerous engine overheating. Additionally, in some aircraft, particularly those with continuous flow fuel injection systems that rely on specific air pressures for proper metering, the cowling helps maintain the correct pneumatic pressures within the engine compartment. And finally, for aircraft equipped with engine firefighting systems, the cowling plays a role in helping to contain the fire extinguishing agent when it's discharged, concentrating it around the engine compartment and augmenting its effectiveness.
So maintaining the cowling and its seals is vital. Inside that cowling, there's a whole network of lines carrying fluids. Let's talk about hoses and tubing, the engine's vital fluid network.
Right. Transporting fuel, oil, air, and sometimes hydraulic fluid requires a combination of rigid tubing and flexible hoses. Flexible hoses are essential wherever there's likely to be relative motion or vibration between the engine and the airframe components it's connected to. Remember, engines are typically mounted on flexible rubber mounts to isolate vibration. These hoses bridge the gap, connecting things like fuel lines from the airframe to the engine-driven pump, oil lines to a remote oil cooler or tank, and pressure lines for instruments or turbocharger systems. Rigid tubing, usually aluminum alloy or stainless steel, is used for plumbing components where there's no relative motion, for instance, between the engine-driven fuel pump and the carburetor if they are both mounted directly on the engine.
What are the critical maintenance points for hoses?
Proper installation and maintenance of hoses are crucial for safety and reliability. Hoses must be routed carefully to protect them from chafing against other components or exposure to extreme heat, like exhaust manifolds. They need to be properly supported with clamps, like Adel clamps, to prevent excessive movement or sagging. A critical point during installation is ensuring the hose is not twisted. A twisted hose is internally stressed and prone to premature failure. Most aircraft hoses have a ley line, a stripe running along their length, specifically to help technicians visually detect any twist after installation. And, as mentioned before regarding any fluid system work, it's absolutely paramount to immediately cap or plug all disconnected lines and fittings during maintenance. This prevents fluid spills, but more importantly, it prevents dirt, debris, or even forgotten tools or hardware from entering the sensitive internal passages of the engine, fuel system, or oil system, which could cause major problems later. This applies even to pneumatic lines.
Good practices. Now, how does the pilot's input in the cockpit moving the throttle, mixture, or prop lever actually translate into direct action at the engine? That seems to be the role of control cables and push-pull rods.
Exactly. These are the mechanical linkages that transmit the pilot's commands from the cockpit controls to the corresponding components on the engine. Depending on the distance and routing, this linkage might be a flexible control cable, a central wire moving inside a flexible outer housing, like a bicycle brake cable but more robust, or a system of rigid push-pull rods connected by bell cranks and levers. Both systems often use specialized end fittings where they connect to the control levers or the engine components. Spherical rod ends, like Heim joints, or ball and socket ends are common, as they allow for slight misalignment and provide smooth, universal movement as the controls are operated. An important safety feature sometimes found on adjustable threaded rod ends is a small witness hole. This hole is drilled through the threaded portion such that if the rod end is screwed onto the push rod correctly, with sufficient thread engagement for strength, the hole will be covered by the rod. If the hole is visible, it indicates the rod end hasn't been screwed on far enough and might fail under load.
You mentioned a safety spring earlier on carburetors.
Yes, and it's worth highlighting again that critical safety design philosophy difference between aircraft and automotive controls. The source mentions the safety spring, often incorporated into aircraft carburetor throttle linkages. Unlike many car throttles that default to idle if the linkage breaks, aircraft carburetors are often designed with a spring that pulls the throttle towards the full open position if the control cable or rod disconnects. The reasoning, as the source points out, is pilot preference. The pilot prefers to have too much power over too little power when desiring to maintain or gain altitude. Even if stuck at full throttle, the pilot can usually still manage the aircraft's descent and shut down the engine using the mixture control lever in its idle cutoff position. This fail-safe to power design prioritizes maintaining flight capability over defaulting to idle. Proper maintenance of these control systems involves ensuring they are correctly rigged for smooth, full range, and friction-free movement. When disconnecting controls during maintenance, they should be lightly anchored or supported to prevent bending or damage. Misadjusting cable ends is a common error to avoid.
That fail-safe design makes a lot of sense in the air. This raises another important question. Performing major work often requires removing the entire engine. How do technicians actually get these complex, heavy machines in and out of the aircraft safely? Engine removal and installation must be a major, carefully planned undertaking.
It absolutely is a significant task, demanding meticulous planning and adherence to strict safety procedures. It's not something done casually. When an engine needs to be removed for overhaul or major repair, technicians must carefully follow the procedures outlined in the specific aircraft maintenance manual. One key aspect highlighted in the source is the critical importance of using the engine's designated lifting points. These are specific, structurally reinforced locations on the engine crankcase or accessory case that are engineered for attaching hoisting equipment, like an engine hoist or crane sling. Using these designated points correctly, often with specific lifting brackets or slings, is crucial to ensure the engine's weight is distributed properly during the lift. Improper lifting, the source warns, could potentially twist or damage the engine structure or cause accessories mounted on the engine to strike the airframe during removal or installation.
What preparation is needed before the actual lift?
Extensive preparation is vital for safety. Before starting the removal process, the aircraft battery must be disconnected to prevent accidental electrical system activation. The aircraft needs to be securely grounded to dissipate static electricity and chocked. Given the potential for fuel or oil spills, appropriate firefighting equipment must be readily available and positioned nearby. The main fuel supply valve must be turned off. And critically, the engine's ignition system must be definitively disabled to prevent any possibility of accidental engine start if the propeller is moved. This goes beyond just turning the magneto switch off in the cockpit. Standard practice involves physically disconnecting the spark plug leads from the spark plugs and ideally removing at least one spark plug from each cylinder, or perhaps removing the distributor caps from the magnetos. You want to be absolutely certain it cannot fire.
Once safety is ensured, fluids like oil and coolant, if liquid-cooled, need to be drained, and the work area kept clean. As components like wires, hoses, control cables, and tubes are disconnected, they must be accurately labeled, and it's highly recommended to create a layout diagram or take photos to aid in correct reinstallation later. A final critical point during reinstallation concerns the firewall, the barrier separating the engine compartment from the cabin. Any openings in the firewall where controls, wires, or lines pass through must be properly sealed using approved grommets, sealants, or fire-resistant fittings. This is vital to prevent the flow of smoke or fumes in the event of a fire in the engine compartment from entering the occupied areas of the aircraft.
That's a lot of critical steps. What happens if an engine is removed or if an aircraft is going to sit idle for a long time? How do you protect the engine from just sitting there? That seems to be where engine storage and preservation comes in.
Exactly. Engines that sit inactive for extended periods are highly susceptible to internal corrosion, primarily caused by atmospheric moisture condensing inside the crankcase and cylinders as temperatures fluctuate. Proper preservation procedures are essential to prevent this potentially serious damage. For engines in flyable storage, meaning the aircraft is flown regularly but perhaps not daily, the source reiterates the importance of operating the engine long enough during each flight to get the oil temperature up to at least 180 degrees AFA and hold it there for about 30 minutes. This heat is necessary to effectively boil off and expel accumulated water vapor from the crankcase oil. Short ground runs are often insufficient to achieve this and can actually worsen condensation problems. For temporary storage, typically defined as up to maybe 90 days or a year, depending on the procedure, more active steps are needed. This usually involves running the engine with special preservation oil mixed in the fuel or sprayed into the cylinders, then draining the fuel system. All engine openings, intake, exhaust, breather lines, must be sealed using non-hygroscopic materials like special moisture-resistant plugs or tapes.
A whistle slot might be cut into the breather plug to allow for pressure changes without popping the seal. Desiccant bags, which absorb moisture, are often placed inside sealed openings. Importantly, the propeller should be placarded with a warning like, "Do not turn propeller, engine preserved." If the propeller is turned for any reason, the preservative oil spray procedure usually needs to be repeated. For indefinite storage long-term, the procedures are even more involved. Regular inspections, for example, every 15 days, are typically required. Desiccant bags need to be checked and replaced if their color indicator shows they've absorbed maximum moisture. Cylinders and valve mechanisms should be periodically inspected, perhaps with a borescope, for any signs of corrosion, and preservative fluid resprayed as necessary. Fuel metering devices like carburetors or fuel injection units often require special flushing and filling with filtered preservative oil, like MIL L6081 grade 1010 mentioned. Care must be taken not to use petroleum-based products and components with rubber diaphragms or seals sensitive to them, like pneumatic chambers and some fuel controls.
That's a lot of specialized care, really highlights that engines prefer to be run. Now, let's pivot to a specific category. Light sport aircraft LSA engines. We see a lot of different engine types in this category. Are they completely different beasts, or are they often adapted versions of what we've been discussing? What are some examples and any specific maintenance points?
That's a great question. The LSA category, along with experimental and ultralight aircraft, often features engines specifically chosen or adapted for their excellent power-to-weight ratio, fuel efficiency, and sometimes lower cost. You see a real mix of specialized designs and clever adaptations of existing technologies. For instance, Rotax engines are incredibly popular in the LSA market. You'll find various models. Some are two-stroke, two-cylinder designs like the Rotax 447UL and 503UL. These are lightweight and simple. Some older two-strokes mix oil directly with the fuel, while others, like the Rotax 503, might use an oil injection lubrication system where oil from a separate tank is automatically metered into the engine. But Rotax also makes more advanced four-stroke engines popular in LSA, like the Rotax 912 series, common variants are 80 key or 100 HP, and the turbocharged Rotax 914. These are four-cylinder, horizontally opposed engines, often liquid-cooled heads and air-cooled barrels, featuring integrated gear reduction drives for the propeller and typically using a dry sump lubrication system. The source also mentions the HKS 700T, another example of a modern LSA engine. It's a four-stroke, two-cylinder turbocharged engine with an intercooler, 4 valves per cylinder, and electronic control fuel injection. Then you have Jabiru engines originating from Australia. Models like the 2200cc 4-cylinder and 3300cc 6-cylinder are four-stroke, horizontally opposed, air-cooled engines known for being very light and having a small frontal area. They typically feature direct crankshaft-driven propellers, no reduction gearbox, simplifying the design.
Jabiru engines often boast fully redundant self-generating electronic ignition systems, meaning they don't rely on battery power for spark once running, and hydraulic valve lifters for automatic valve clearance adjustment, reducing maintenance. They also commonly use standard automotive spin on oil filters and offer options like a vacuum pump drive pad. You'll also encounter engines based on automotive designs, like the Great Plains Aircraft Volkswagen VW conversions. These are adaptations of the time-tested air-cooled VW flat-4 engine, typically modified for aircraft used to produce between 60 and 100 horsepower. They are popular in the home-built and experimental market due to their relative simplicity and parts availability. And finally, you also see certified, more conventional aircraft engines being used in some LSA designs, like the reliable Continental O200AB. This is a classic four-cylinder, four-stroke, horizontally opposed, air-cooled engine with a wet sump lubrication system and typically a carburetor, though fuel-injected versions exist. It's heavier than some specialized LSA engines, but known for its robustness.
So quite a variety. What about maintenance? Are there specific practices emphasized for these? Maybe using Rotax as an example since they're so common?
Yes, while basic principles are the same, specialized LSA engines often have very specific maintenance requirements outlined by the manufacturer, and strict adherence is crucial. The source uses Rotax maintenance as an example to highlight some typical practices. Firstly, there's often a strong emphasis on adhering strictly to the manufacturer's recommended inspection schedules and procedures. For instance, the source notes that for Rotax, the 100-hour inspection interval often carries a tolerance of plus or minus 0 hours for calculating the next interval. This means if you perform a 100-hour check at, say, 110 hours, the next one is still due at 200 total hours, not 210. Following the exact schedules and checklists is paramount. For multi-carburetor Rotax engines like the 912 series, carburetor synchronization is a critical maintenance task for achieving smooth idling and balanced power delivery between cylinders. This typically involves both a mechanical synchronization, adjusting the Bowden cables connecting the throttles to ensure the throttle valves open simultaneously, and a pneumatic synchronization, using vacuum gauges or flow meters connected to ports on the intake manifolds to precisely equalize the airflow vacuum at idle. Fine-tuning the idle speed and idle mixture adjustment screws on the carburetors is also part of routine maintenance for optimal running. An oil change procedure on a dry sump Rotax engine has specific steps. After warming the engine and draining the oil from both the tank and the crankcase and replacing the filter, the source emphasizes the need to manually crank the engine by hand, propeller removed, ignition off, for approximately 20 turns. This helps draw oil from the tank and refill the internal oil pump and circuits, purging air before the engine is actually started. Importantly, it stresses not using compressed air to try and force oil through, as this can introduce air pockets or potentially damage seals. Regular magnetic plug inspection, as we discussed earlier, is a specific routine check for engines like Rotax, often in the oil tank or gearbox, and Jabiru in the crankcase sump. Checking this plug for accumulated metal chips provides a direct indication of the internal condition of the gearbox for Rotax or engine wear. The type and quantity of chips found dictate the necessary follow-up action. For Rotax engines with integrated propeller gearboxes that incorporate an overload clutch, specific checks like measuring the friction torque required to turn the gearbox freely are performed to assess the condition of the clutch mechanism. Engine preservation procedures for short or long-term storage are also specifically detailed by manufacturers like Rotax, often involving injecting preservation oil into carburetors and cylinders, turning the crankshaft by hand to distribute it, draining fuel and coolant, if applicable, and sealing all openings. And finally, spark plug inspection remains vital for all engine types. The appearance of the spark plug tip provides valuable clues about the engine's combustion health. A light brownish tan color usually indicates correct mixture and heat range. Black, velvety soot points to an overly rich mixture. Oily deposits suggest excessive oil consumption, possibly due to worn piston rings or valve guides. The source specifically warns against using steel or brass wire brushes, or abrasive methods like sandblasting to clean spark plugs, as these methods can damage the delicate insulator or electrodes, potentially causing misfires later. Proper cleaning methods recommended by the manufacturer should always be used.
Wow, okay. What an incredibly detailed journey through the amazing world of aviation piston engines, from, the microscopic movements of sodium sloshing inside a valve stem to the really complex interplay of atmospheric pressure, fuel systems, and digital controls. We've really peeled back a lot of layers today.
We really have. And if we connect this all back to the bigger picture for you, the listener, hopefully you now have a much deeper appreciation for not just how these incredible machines work, but why certain design choices were made over others, and what it truly takes in terms of precision manufacturing, careful operation, and diligent maintenance to keep them performing safely and reliably in the air. This knowledge isn't just for aviation technicians. I think it fundamentally transforms how you perceive these engines, especially when you stop and consider something like that spark plug, enduring thousands of degrees, immense pressure, massive voltage, and doing its job perfectly dozens of times every single second.
Absolutely. So, knowing now just how delicate that balance is, air, fuel, pressure, temperature, and the constant battle against the elements and the laws of physics, what do you think the next great aha moment might be for piston engine technology? As engineers continue to push the boundaries of efficiency, reliability, maybe even alternative fuels, in a world that's constantly seeking cleaner and smarter ways to fly, what's the next horizon look like?